Good morning. Today we are going to discuss about ideal and non-ideal solutions. Ideal solutions and non-ideal solutions. First, let's discuss about ideal solutions. Ideal solutions are solutions which obey Rawls' law over the entire range of concentration. Therefore, for an ideal solution, PA is equal to P naught A into XA and PB is equal to P naught B into XB because they obey Rawls' law over the entire range of concentration. Now the second point is an ideal solution, the enthalpy of mixing is equal to 0. And we know we denote enthalpy with delta H. So enthalpy of mixing for an ideal solution is equal to 0, which means that when you mix two components, there is no evolution of heat or absorption of heat. So their enthalpy of mixing is equal to 0. Now the third point coming under ideal solution is the volume of mixing is equal to 0. So delta V mixing is equal to 0. That is, when you mix the components, the total volume of the solution will be the sum of volume of all the components present. So there is no change in volume when you mix the components. That is, delta V of mixing is equal to 0. Now, the last point coming under ideal solution is, we know that a solution means we have a solute and solvent. So there are mainly three types of forces present in a solution. One is the force of attraction between solvent molecule. Second is the force of attraction between solute molecule. And third is force of attraction between solvent and solute molecule. So suppose this is an ideal solution. In that case, we can say that the force of attraction between solvent-solute molecule will be equal to the force of attraction between solvent-solvent and solute-solute molecule. Or we can write this as the force of attraction between AB, solvent-solute molecule, is equal to AA and BB. That is the force of attraction between solvent-solvent and solute-solute molecule. Actually, it is very difficult to observe an ideal solution. But there are examples where the solutions behave as ideal solutions. And the examples are, the example for ideal solutions is normal hexane and normal heptane. Next example is benzene and toluene. And the third example is bromoethane and chloroethane. So these are the three examples for an ideal solution. So for an ideal solution, we can see the ideal solution obeys Rawls' law for the entire range of concentration. The delta H of mixing is equal to 0. Delta V of mixing is equal to 0. The force of attraction between AB is equal to AA and BB. And three examples for ideal solution. Now let's see what is a non-ideal solution. Non-ideal solutions does not obey Rawls' law over the entire range of concentration. That means PA not equal to P naught A into XA and PB not equal to P naught B into XB. Now, their enthalpy of mixing is not equal to 0, which means there will be a change in temperature on mixing the components of an non-ideal solution. Now, their volume of mixing is also not equal to 0. And the force of attraction between solvent and solute is not equal to force of attraction between solvent and solute molecule. And example for non-ideal solution is ethanol acetone. Second example is phenol aniline mixture. So these are the properties of a non-ideal solution. They do not obey Raoult's law over the entire range of concentration. Their delta H of mixing is not equal to 0, delta V mixing not equal to 0, and AB interactions are not equal to AA and BB interactions. Now let's see about non-ideal solutions. So we can classify non-ideal solutions into two types. One is non-ideal solutions showing positive deviation from Raoult's law, and non-ideal solutions showing negative deviations from Raoult's law. So next we are going to discuss about non-ideal solutions. The first one is non-ideal solution showing positive deviation from Raoult's law. Now, I told you non-ideal solution means solutions which do not obey Raoult's law over the entire range of concentration, which means the vapor pressure of such a solution will be either higher or lower than that expected by Raoult's law. Now, non-ideal solutions are divided into two types. Solutions which show positive deviation from Raoult's law. In this case, the vapor pressure of the solution will be higher than that expected from Raoult's law. Now let us see the cause for this deviation from Raoult's law. The reason for the deviation from Raoult's law is in solutions showing positive deviation from Raoult's law, the AB interactions, means solvent-solute interactions, are weaker than solvent-solvent and solute-solute interaction. So this is the cause or reason for non-ideal solutions showing positive deviation from Raoult's law. That is, the molecular attraction between solvent-solute is weaker than solvent-solvent and solute-solute interactions. Which means if the force of attraction between solvent-solute is weak, then the molecules will find it easier to escape into vapor state. As a result, the vapor pressure increases. And that increase will be greater than that expected by Raoult's law. So we say that such a solution will show positive deviation from Raoult's law. For example, the example for solution showing positive deviation from Raoult's law is ethanol acetone mixture. Ethanol, we know the formula of ethanol is C2H5OH. This is an alcohol, and acetone is CH3COCH3. Now, in ethanol, there is a strong hydrogen bonding present. Now, when you add acetone to ethanol, the hydrogen bonds become weak. Because we are adding acetone to ethanol, the hydrogen bonds in ethanol will become weak. As a result, the force of attraction between acetone-ethanol molecule become weak, and more molecules, ethanol and acetone, can go into vapor state. And as a result, the vapor pressure increases. And that increase is greater than that expected from Raoult's law. So we say that ethanol-acetone mixture is an example for a non-ideal solution showing positive deviation from Raoult's law. Now, the second example for non-ideal solution showing positive deviation is carbon disulfide and acetone mixture. Example 2 is carbon disulfide and acetone. Now in this case also there is a weak force of attraction. When you mix carbon disulfide and acetone together, there is a weak force of attraction, and as a result more molecules can go into vapor state and vapor pressure increases, and they show positive deviation from Rawls law. So these are the examples for non-ideal solution showing positive deviation from Rawls law. First one is ethanol acetone mixture, and second one is carbon disulfide acetone mixture. Now when you draw the graph for non-ideal solution showing positive deviation from Rawls law, we know that the graph of Rawls law for a volatile liquid. Now that is the graph that is expected for an ideal solution. So I'm going to draw that graph again. This is the graph we drew for vapor pressure against mole fraction. Here we have XA is equal to 0, XB is equal to 1. Here XA equal to 1, XB is equal to 0. And here we have P naught A, P naught B, this is PA, PB, P total, which is equal to PA plus PB. Now this is the graph of an ideal solution, means this is the graph of our Rawls law for a volatile liquid, and this is the graph for an ideal solution. Ideal solution means solutions which obey Rawls law over the entire range of concentration. Now suppose the non-ideal solution shows a positive deviation. In that case we know the vapor pressure of the solution will be higher than that expected from Rawls law. So when we draw the graph for a non-ideal solution showing positive deviation from Rawls law, the graph will be like this. The ideal solution graph is drawn and the partial pressure of each component will be higher. See, the partial pressure of component A increases, the vapor pressure of component B increases, the total vapor pressure of the solution also increases. So this is the graph for non-ideal solutions showing positive deviation from Rawls law. Now let us discuss about the second type of non-ideal solutions. That is non-ideal solutions showing negative deviation from Rawls law. Now in this case we can see that again this is a non-ideal solution, so it is showing negative deviation from Rawls law. Now in this case the vapor pressure of that solution will be lower than that expected from Rawls law. So solution which shows negative deviation from Rawls law has a vapor pressure lower than that expected from Rawls law. So in this case the cause for this deviation is AB interactions will be stronger than AA and BB interactions. That is, the force of attraction between solvent and solute is stronger than that between solvent-solvent and solute-solute. So we know if the force of attraction between solvent and solute is stronger, then the molecules will find it difficult to escape to the vapor state. As a result, the vapor pressure decreases, and the decrease is lesser than that expected from Rawls law. So this is non-ideal solution showing negative deviation from Rawls law, where we have AB interactions greater than AA and BB interaction. Now example, there are two examples. The first example I'll explain with chloroform and acetone. First example for non-ideal solution showing negative deviation is chloroform and acetone. Now, you know acetone is CH3 COCH3, and chloroform is CHCl3. So I am writing the structure of chloroform. This is chloroform. Now, when these two molecules are mixed together, a strong hydrogen bond exists between these two molecules, and this bond formed is very strong, which means these two molecules cannot easily escape into vapor state. Vapor pressure decreases than that expected from Raoult's law. Now, the second example for non-ideal solution showing negative deviation from Raoult's law is between phenol and aniline. Phenol and aniline. Now, when phenol and aniline are mixed together, you know the structure of phenol. Phenol is C6H5OH. And aniline formula is C6H5NH2. And in aniline, there is a lone pair of electron on nitrogen atom. Now, when they are mixed together, a strong hydrogen bond is formed between phenolic proton. This is the phenolic proton H+, and the lone pair on nitrogen atom. So, as a result, the bond is very strong, which means it is difficult for these two molecules to escape into vapor state. So, vapor pressure decreases than that expected from Raoult's law. So, we can say this solution, phenol aniline mixture, shows negative deviation from Raoult's law. So, these are the two examples for solution showing negative deviation from Raoult's law. The first example is acetone and chloroform. Second is phenol and aniline. Now next, let's see the graphical representation of non-ideal solution showing negative deviation from Raoult's law. For this again, we have to draw the graph for an ideal solution first. So I'm going to draw the graph of ideal solution again. The graph of an ideal solution. We have vapor pressure here, mole fraction, and first we have the component A, where XA is equal to 0, and here we have XA is equal to 1, maximum value P0A. Now for component B, we have XB is equal to 0, XB is equal to 1. This is for component A, partial pressure. This is the partial pressure of component B. Now the solid line represents the total pressure. This is the graph of an ideal solution. Now, if it's a non-ideal solution, we know that non-ideal solution showing negative deviation, the vapor pressure of the solution will be lower than that expected from Raoult's law. So, when we are showing the negative deviation, you have to show negative deviations like this. So, the solid lines represents that vapor pressure of the solution is lower than that expected from Raoult's law. So this is the graphical representation for non-ideal solution showing negative deviation from Raoult's law. Now next we have a term called azotropes. Azotropes. Now, what are azotropes? They are binary mixtures having same composition in liquid and vapor state. Binary mixture having same composition in liquid and vapor state, and they boil at constant temperature. This is azotrope. So azotropes are binary mixtures having same composition in liquid and vapor phase, and they boil at constant temperature. So since the binary mixture means two liquids together, since they boil at constant temperature, it is very difficult to separate this azotrope by fractional distillation. Now, we can say that solutions which show positive deviations from Raoult's law form minimum boiling azeotrope, and solutions which show negative deviations from Raoult's law form maximum boiling azeotrope. So we can say solutions that show positive deviation from Raoult's law will form minimum boiling azeotrope. Minimum boiling azeotrope means the boiling point of that mixture will be lower. Okay, boiling point lower means vapor pressure will be higher. So we know that positive deviation means they have larger vapor pressure. So they form minimum boiling azeotrope. An example for this minimum boiling azeotrope is ethanol water mixture. That is the example for minimum boiling azeotrope. Ethanol water mixture. So we know that ethanol and water, when they mix together and heated, we get, at some point we get an azeotropic composition. Azeotropic composition means that mixture, ethanol water mixture, will boil at same temperature. We know that ethanol has a different boiling point and the boiling point of water is also different. But when we mix these two and boil, at some point we get an azeotropic composition. Azeotropic composition means at that point this mixture will boil at a particular temperature. That means at a single temperature. Okay, and at this point, at this azeotropic composition, it is difficult to separate ethanol and water. So we can say that is an example for minimum boiling azeotrope. Means these mixture will boil at a temperature below the boiling point of individual components. Means suppose ethanol boiling point is 351.3 Kelvin. 351.3 Kelvin and the boiling point of water is 373 Kelvin. Now when they form an azeotropic composition, they will boil at a common temperature, and that common temperature is 351.15 Kelvin. So this is the azeotropic composition or azeotropic temperature of ethanol water mixture. So in this temperature, it is difficult to separate ethanol and water. So that is the meaning of minimum boiling azeotrope. That is, that mixture will boil at a temperature lower than the boiling point of individual components. That is ethanol and water. You can see this temperature is lower than this and this value. Okay, so solutions which show positive deviation from Raoult's law will form minimum boiling azeotrope. Now, solutions which show negative deviation from Raoult's law, negative deviation, will form maximum boiling azeotrope. Maximum boiling azeotrope means their boiling point will be higher, and which means the vapor pressure will be lower. So the relation between vapor pressure and boiling point, they are inversely proportional. So solutions which show negative deviation from Raoult's law will have maximum boiling azeotrope. And an example for solutions forming maximum boiling azeotrope is nitric acid water mixture. So an example for maximum boiling azeotrope is nitric acid and water mixture. So these examples are also very important. Example for maximum boiling azeotrope, nitric acid and water, and they show negative deviation from Raoult's law. So this is about positive non-ideal solutions showing positive and negative deviations from Raoult's law, and also about azeotropes. Thank you.